So, questions up to here. So I posted an ODP this morning and I accidentally made the README non-readable. So I fixed that an hour ago. Unrelated to that, I decided to give you until 5 o'clock tomorrow for the ODP, 5 p.m. So it's more like a day and a half program. So that works out well. So
I kind of did it in the first hour.
Okay, cool.
Yay me.
Yay. Yeah, I kept looking this morning. I'm like, nobody's done this yet. I wonder why. All right, so let's look at 241. And we have a new bulb in our projector. That's why we can like do this with the lights on. And that was Scott's observation. He was in a class last week and noticed that their screen was really bright. And he said something about it in class, and Khan from the previous section who works at IT heard this, and he's like, well, I'll talk to IT. And so I guess 20 days later they replaced this bulb in here so we can have the lights on and still see the screen. So that's cool. All right, so ODP 241 due tomorrow evening around 5, I think. Check Canvas for the due date. So it's working with a try. It's using the same try-node structure that you used in 240. But in this case, you're making a function called findWord. It takes the root of a tree and it takes a string, okay, which I'm calling word here. So it's a character array. And it looks for that word in the try. If it finds it, it returns a 1. If it doesn't find it, it returns a 0. So instead of looking to see if that single character is not null, it's looking for a whole word. And to do this, you basically work with the try structure that you were working with yesterday. So here's our root, which I'm passing to you. And let's say you're looking for the word dog. Yay! Dog and cat. So take the first letter of the word, check the pointer in the root, okay, same as you did for ODP 240. If that points to a node, move to the second letter, check that letter's pointer in that new node, assuming that points to a node. Move to the third letter, check that letter's pointer in the node, assuming that points to a node. You're at the end of your word, so now check that end of string integer and make sure it's a 1. If all of that happens, then you know that this word is in your structure. If this is not a 1, or if any of these pointers are pointing to null, you can stop right there and say this is not a word in the structure. Because if you have a null pointer and you try to find what O is pointing to, you'll segfault. So as soon as your pointer is null, you're done, return a 0. If you get all the way to the end of the word and that integer is not a 0, you're done, return a 0. Otherwise, return a 1. Make sense?
So basically you go through the thing, and if the last thing you don't find is in the last line is in P1, it's no.
Mm-hmm. Yeah, so for example, if we had the word dogs stored, then this S would point to another node, and this would be a 1. But we go D, O, G, we check this, we'd see a 0, we'd say dog is not stored in there. If we were looking for dogs, we would have followed the S down, and then we'd see that end of string is a 1, we'd say dogs is in there. And if this happens to be a 1, then we have both dog and dogs. So it's a loop, right, for I equals 0 to length of your string minus 1. And inside that loop, just follow these pointers. If at any point you follow your pointer to a null, just return 0. If you get to the end of the loop, see if the thing that you're pointing at has an end of string set to 1. If it does, return 1. Otherwise, return 0. So that is described in here. That's what all of this is saying. So link it up with main 241. Go ahead and assess it. Let me take a peek and see how many people have done this. I don't have a connection. That's okay. All right, makes sense? All right, and I won't post an ODP tomorrow, obviously, because it's the weekend. So I'll probably post an ODP next week to have you insert something into a try. And if you can search, insert is just really one sort of extra step that you have to take, which is as you're going through looking for this, when you get to something that points to null, then you just start creating nodes, and you move down and you create nodes and continue. And then you set the end of string marker to 1. All right, so changing gears here, we're going to come back in a few weeks and talk more about trees. After you turn in PA4, we'll go ahead and we'll look at some code for doing balancing of Avl trees, so doing those rotations, because it's pretty cool how you can code that up. We'll also look at another version of a balanced tree, which is called a red-black tree. And red-black trees are very different from Avl trees. They're not at all balanced in the usual sense of balanced, but they still perform really well. And we'll spend a day looking at those and playing around with them. But for now, I want to talk about sorting. And the basic goal of sorting is just you have a set of data and you want to organize it in some kind of order, increasing or decreasing. And we can sort pretty much anything that we want: words, numbers, movies, binary files, right? As long as we have a way to compare any two of these things and say which one is greater than the other. So we need to have some way to do a comparison. For integers, we typically just compare to see which one's larger. For strings, we usually compare letter by letter, and wherever the letters disagree the first time, we take whichever one has, say, the larger ASCII code. That's the one that's greater. And the string compare function does that for us. Okay, that's exactly what it does. But we can sort anything as long as we have a comparison function. So we could take JPEG images, and we could look pixel by pixel and find the first pixel starting from the upper left, going across and scanning down until we get to a pixel that's different, and we could pick the one with the largest intensity of red or green or blue and say that's the one that's greater than the other. So we're gonna stick with integers, right? But keep in the back of your mind we can apply these algorithms to pretty much anything, as long as we have a way to compare. So quintessential sort is Bubblesort. And you've done this in 121. We use this in 224 in our dictionary code. But it's a good sort to start with. And it's a good sort to use to analyze order of complexity. And this is going to be one of our goals in talking about sorting, is understanding how complex these sorts are time-wise. How much time do we need? And so we're going to spend some time talking about order of complexity. I'm going to make some notes. So what's the classic bubble sort? Classic bubble sort, we take our data, we move through from the beginning to the end, and we swap pairs of numbers that are in the wrong order. So let's say our goal is to have the smallest number at the top and the largest number at the bottom. Okay, we make one pass through our data, and we swap things that look like they're in the wrong order relative to each other. So we want smaller numbers on top, so 24 and 12, those are backwards. The 12 should go on top. 24 should go here. 24 and 11 are in the wrong order, so we should swap those. So 11 goes here, 24 goes there. 24 and 30, that's the right order. 30 and 6 are in the wrong order, because 30 is bigger, so that should get swapped. So 30 comes down here. 30 and 5 are in the wrong order, so swap the 30. 30 and 40 are in the correct order. 40 and 10 are in the wrong order, so swap those. And there's the result of our first pass. So we make one pass, and the goal of the pass is to move the largest element to the bottom. So you picture these things falling in water, and the heavy things sink and the light bubbles rise up. Okay, so that's the bubble, part of a bubble sort. So we make one pass, the largest element comes down to the bottom. Well, once we know that the largest element is in the bottom, that's not going to move. That's in the correct spot for our final sort. So we can just pretend that's not there and say we've got this smaller set of elements. If we make the same pass through here, the largest element in this set is going to end up at the bottom of this set right here. So if we make a second pass, 12 and 11 will swap, 24 and 6 will swap, 24 and 5 will swap, 24 and 30 stay the same, 30 and 10 swap, right, and we didn't touch anything with the 40. Right, so now we've got that 30 in the correct spot. And if we do one more pass on this, right, the 11 and 12 stay the same, 12 and 6 swap, 12 and the 5 swap, 24 is correct, 24 and the 10 swap, and now we've got our 24 in the correct spot. And so each pass you have fewer and fewer numbers to sort. And so assuming that we have n numbers, so if we do n passes, we should end up with our entire collection of data sorted. And each time we make a pass, we don't really care what happened up here. Right, 12 and 11 are in the wrong order, 6 and 5 are in the wrong order, 30 and 5 are in the right order. We don't really care about that. All we care is that each time we do a pass, we've got one more number in its correct spot. And there's stuff happening up above, which we're not going to worry about until a later pass. So if you code this, it usually looks something like this. So for pass equals 1 to n, for I equals 1 to n, this is pseudocode. Don't worry that I'm starting from 1 instead of 0. And then, so compare element I to I plus 1 and swap if out of order. So this inner loop, this single pass, we're basically doing n steps, where this is what I'm calling one step. So a step is comparing an element to the element after it and then swapping if they're out of order. So our inner loop does a total of n steps, And our outer loop says do the inner loop n times. So this is n inner loops. So what's the total number of steps that we're going to do? N squared. So Bubblesort, we're doing this inner piece where we do our comparison and possibly swap roughly n times, n squared times, for n numbers. So good so far? Yeah.
If you're breaking out early, doesn't it become n factorial?
I hope not, because that's way worse than n squared. But we can make it better than n squared. I think you're thinking 1 plus 2 plus 3 plus n.
Okay.
Yeah. So we're heading there shortly. All right, so we can start tweaking the code, right? For example, we don't really need to go through all n elements in this inner pass. We actually need to go through n minus 1, because we're comparing an element to the element after it. We only have to do that n minus 1 times. And we only need to do a total of n minus 1 passes, because once we have n minus 1 things in the correct spot, we know the last remaining thing has got to be in the correct spot also, because it's only got one place to be. So we could drop this down to, say, n minus 1 times n minus 1. And we can do a lot better than that. So the first time through, we're doing n of these inner steps. The second time through, we only have to do n minus 1, because we don't have to deal with this last element. The next time through, we're doing n minus 2. The next time through, n minus 3. So with this first order analysis, the total number of steps was basically n plus n, a total of n times, which was n squared. But with just a little more coding, it's actually n plus n minus 1 plus n minus 2. Right, it's actually just the sum of these values. Do you remember what this sum is? 215 test. Smaller than that, it's polynomial. So sum of consecutive integers. Do a quick inductive proof in your head. Yeah. Plus 1 or minus 1. I always have to plug in 3 to see which one it is. I think it's n minus 1, just because we did this an hour ago. 3 times 2. Maybe it's plus 1. 3, 1, 2, 3, 6, 3, 4. Yeah, you're right, it's plus 1. Good. So we're going to talk about this thing called big O notation, which we write as the script O. And we're going to say that a bubble sort is order n squared. And this means the time required for the algorithm.
Does that say n minus 1 in parentheses or n plus 1?
Here?
Yeah.
Plus 1. So order n squared means the time required for the algorithm is approximately n squared, where n is the size of the data, or the amount of data. So n squared what? N squared seconds, n squared microseconds, n squared years? Don't know. Okay, so this is the first thing about this big O notation. We're not talking about time, we're talking about numbers of steps, where the idea of step is kind of loosely defined. So our step in a bubble sort is to compare two things and swap them if they're out of order. And you know, sometimes they're going to be out of order and we're going to have to swap. Sometimes they'll be in the correct order and we don't have to swap. It's going to be faster if we don't have to do that swap, because a swap takes 3 assignment statements. But we're not worried about those details of is this going to take 5 steps or 2 steps, right? The number of times that we're doing this inner part of our code is basically n squared. And on average, right, if our data is completely out of order, we're going to end up doing the swap again and again and again. If our data is perfectly ordered, we're never going to have to do the swap. But on average, right, maybe we'll swap half the time. It's not going to change the fact that this is basically order n squared. But if we do this embellished sort, it's actually n squared plus n over 2. Which seems, you know, a whole lot better than n squared because it's roughly half what it takes for the unimproved sort. So let me show you what this order of complexity actually means. So suppose we have n pieces of data, and suppose we have our naive bubble sort, which takes n squared steps. And then we have our improved bubble sort, which let's just say takes n squared over 2 steps. We'll forget about that plus n for a moment. Okay, if n is equal to 2, this first bubble sort is going to take 4 steps. The fancy one's only going to take 2 steps, half as many. If n is 4, basic bubble sort's going to take 16. Fancy bubble sort's going to take only 8. If n is 20, plain bubble sort's going to take 400, fancy bubble sort only 200. Clearly the fancy bubble sort is doing less work compared to the plain one, right? But that's not what we're trying to capture. What we're looking at is when we increase n, how does the number of steps increase? Okay, so here we've doubled the amount of data. Here our number of steps went up by a factor of 4. Here our number of steps also went up by a factor of 4. Here we've got 10 times as much data. Here the number of steps went up by 100. Here the number of steps also went up by 100. It's this increase that we're interested in. When I have 10 times as much data, the time required goes up by 10 squared. Okay, so that's what we're capturing when we say something is order n squared. Means if you double the data, you quadruple the time required. And that division by 2 doesn't change that factor. It means it's going to take less actual time, but the increase in time is still going to be 100x if we have 10 times as much data. So we can rightfully say order of n squared is the same as order n squared over 2. And in fact, it's the same as order n squared over 1,000. And it's the same as order 1,000 times n squared. So constants don't matter when we're looking at order of complexity. We can throw them away, and we usually just make the constant a 1. Okay, the second thing is, what about this plus n? So this should be the same as order n squared plus n. And I'm going to claim that this is the same as order n squared. Because we're looking at asymptotic behavior, we're looking at this as n gets really big. And that should make sense, because if n is 1, if you use a bubble sort on a single piece of data, right, it doesn't take a whole lot of work. It's an outer loop of 1 pass, an inner loop of 1 pass. There's nothing to swap because this array of 1 number is already sorted. But it's still going to take a lot of time to do that code, because you've got to initialize your array, you've got to do some mallocs, you got to start your program, you got to go through these for loops and see that you're done, and so on and so forth. So for small n, right, your time may not look the same, may not look as close to n squared as it does for a bigger n, right? Now, if n is a gazillion, and I'm going to do a gazillion squared operations, the fact that it took me 5 microseconds to start my program is not going to change how much time it takes in the end, because it's going to take, 15 years plus 5 microseconds, right? But if my n is 1, it's only going to take me 10 microseconds to do my sort, and I've got 5 microseconds of startup, right? That's going to affect my time more. So as n gets bigger and bigger, this plus n becomes smaller and smaller of a factor. And so we're really looking at kind of a limit as n goes to infinity. And these smaller terms in the polynomial will go away. So order n squared plus n is going to be the same as order n squared. So if you have a polynomial order of complexity, usually we just take the highest coefficient, right, the highest powered term, we make a coefficient of 1. And we call it n squared in this case. Okay, another thing to keep in mind about these orders of complexity, they don't map directly to time. If I do this on a 1960s computer, or I do this on a modern supercomputer, the amount of time is going to be radically different. Right? But they're still the same order of complexity. Because maybe in the 1960s this took, 2 days, or, 2 took 4 days versus 400 days. And maybe today it's 4 microseconds versus 400 microseconds, right? The increase is still 100x. So the amount of time doesn't actually matter. It's the increase in time that we're looking at. And the other thing is, for us, these are averages. Because if I make a really good bubble sort, I can short circuit this outer loop by saying, hey, if I don't swap anything on this inner pass, I'm done. And instead of just blindly making n passes through my data, each time I go through, I'll see if I swap anything. As soon as I don't have to do any swaps, I don't need to make any more passes. So I can change this outer loop to a while loop. When I swap, I can set a flag, and I can say, while this flag is set, showing that I swapped something, do another pass. And now if my data is sorted to begin with, I make 1 pass and I'm done. So my best case is going to be order n. My worst case is going to be order n squared. My average case may be n squared over 2. But for us, we're going to mostly concentrate on average case, because the pathological best and worst cases are sometimes fundamentally different. So we're not going to worry about those little details. So we're going to use this big O concept as a way to sort of analyze different types of sorts. A way to kind of compare and contrast. And it's not a universal meter stick, because sometimes there's an algorithm with a worse order of complexity, but it's going to work better for your situation. And there's reasons that we'll talk about in a little bit why that might happen. All right, so you know Bubblesort, right? Main thing to remember, Bubblesort is order n squared. Let me give you 2 other versions of sorts. There's a selection sort and an insertion sort. And the difference between them is basically where the sorting is taking place. So in both of these, you're going to start off with an array of data, and you're going to end up with a new array of sorted data. So you're moving stuff from an unsorted array to a sorted array. And we can mimic this with playing cards. So I've got a set of cards, and we're going to sort them. So here's our input array, here's where our output array is going to be. And we're going to move cards from here to here so that we end up with a sorted list over here. Okay, a selection sort, we pick cards from the input. in sorted order. And insertion sort, we place cards in the output in sorted order. So selection sort, we're selecting cards in a particular order. Insertion sort, we're inserting cards in the output in a particular order. So it's kind of where the sorting has happened. So let me just show you with cards what a selection sort would do. Take your input deck, find the smallest number. So, right, set something equal to the smallest, move through and compare each thing to it, keep track of the smallest. When you're done, decided an ace was the smallest, I'm going to take that, put it in my output. Now go through, find the smallest thing in your input. So it looks like 8, looks like 7, 3, looks like 2. Right, so I select my smallest and I just put it in the next place in the output array. So placing in the output is a really simple operation. I just add it to the end of the array. All the work is happening, and when I select which card to move to my output. So find the smallest, looks like an 8, 8, 8, 7. There's a 3 is the smallest, 3 is the smallest. Take that, put it in your output. Okay, so all the work's happening on the selection side. 8, 7, there's a 4 is the smallest. And you just keep doing this. And obviously if you have n pieces of data, you're going to have to do n passes. And when you're done, your output should be sorted. Magic. All right. Insertion sort, we're not going to do any work when we pick cards. We're just going to grab the top card off the deck. So we're just going to take this card, we're going to put it in our output in the correct spot. Well, there's nothing in our output yet, so it goes there. All right, pick the top card, insert it into the correct place in your output deck. That should go right there. Take the top card, insert it in the correct place, goes right there. Top card inserted in the correct place. Top card inserted in the correct place, so that's going to go right there, and so on. All right, so find a way to remember which of those is which, and put it in your note sheet, because I usually ask you to do both on a test, but I might just ask you to do one. So what's a selection sort look like? Each time that we go through the body of this process, right, we're choosing the next card from our input and then copying it to the output. So our inner loop is like something like this, for I equals 1, 2, and n's getting smaller. That's okay. If data I is smallest, remember it. So go through all your cards, remember the smallest one, and then move the smallest to the output. And this whole thing gets done for n passes. So for your pass equals 1 to n, do this inner loop where we pick the smallest thing, copy it to the remember which one it is, and then when we're done, copy it to the output. So inner loop n times, outer loop n times, this is order n squared. Insertion sort, take the top card, So, the first thing in your data. And we have to place it into the output array in the correct order. So for I equals 1 to n, if output I is bigger than data, insert before output I. This is what you did with your linked list, right? So if here's your output array, and you're trying to place an 8, go through your input until you find something bigger than 8. That's right there. Insert right before. Okay, that's just your linked list insert. So this is order n, and you have to do this for n passes. So this is also order n squared. So Bubblesort, Selection Sort, Insertion Sort, all nominally n squared. Roughly the same complexity. And if you want to actually code this, what does a selection sort look like? So here's your data array. So how do we pick the smallest element out of an array? Start off with the first element being your smallest, and then loop, say, from element 2 to n. This is still pseudocode. You'd normally start from 0. So go through all the other elements, and if data index I is less than smallest, then we've got a new smallest. And when we're done, smallest is the smallest. So add that to our output. Well, arrays in C, we've got to keep track of how long they are. So we also need some sort of output length. So initialize output length to 0. So down here we can say out element output length plus plus equals smallest. And do that n times. And there's one piece of this that's going to make the thing break the way it's written. Because right now, every time I go through, I'm going to find the same smallest number, right? Because I'm not actually taking anything out of my input array. So after I find the smallest number, I need to somehow remove it from my input array. So there's a variety of ways to do that. One way is, instead of just making an array of integers, use a structure where you have an integer and a flag saying whether that integer has already been taken out of the array or not. So like a valid bit somewhere, which means that when I find the smallest element in my array, I also need to save the index where that element's found. Just what?
Just put that element in a while loop, and then once you pass it in out, have the first thing, instead of being a 1, be a variable.
Mm-hmm.
And then you increment that variable at the very end of that.
Mm-hmm.
So that way every time you're looking at the next position after that,
Okay.
that's your starting point.
And you got to do one other thing too, but you're right there. You also want to swap your smallest with the first element so that you don't consider it again. So this is a really slick way to do this. Let me show you the non-slick way first, and then we'll do the slick way. So non-slick way, we could remember the location of that smallest number, and then when we get to the end, copy it to the output array, and then data, smallest index, dot valid equals 0. And up here, when we're comparing element I, just make sure that its valid is equal to 1. Right, so we're effectively taking things out of the array. But a better way would be to do the same thing, but when we find the smallest element, we could swap it with the first element in our array. And then in this inner pass, instead of always starting from 1, we could start from whatever the next element is. Right, so we basically move the numbers we've already used out of contention. And we don't have any assumption on the sort order of this input array, so moving things around is not a problem. And that's a really slick way to do this, because now you can just use plain integers, and it takes care of not counting the same thing twice. So there's different ways to code this. And I mentioned briefly in the last section, if you go back, several decades, before hard drives were really a thing, data was stored on magnetic tape. And so magnetic tape, if you've seen like 1960s sci-fi movies, right? You have a plastic spool. It's a really bad drawing of a magnetic tape with tape wound up on it, and it comes over onto another spool over here. And you can write 1s and 0s onto this tape. It's usually got multiple tracks, so 8 tracks, 16 tracks, something. But you can write 1s and 0s by magnetizing, okay? Think cassette tapes. And you have a spindle of tape over here, several thousand yards of tape maybe. And you have a spindle over here that starts off empty, and as this turns, tape moves over here and wraps up. Okay, it's really good for storing a lot of data. It's very inexpensive, very reliable, and it's not too slow unless you're sitting here and you want something that's stored in the middle of this tape. Then it's really slow, because I have to spin a few thousand yards of tape onto this reel just to get this piece of tape right here to come into the middle where I have my read-write head, and then I can read my 3 bits of information that I wanted. And I say, okay, I want to add that to the end of my array. So now I have to spin this the rest of the way to get to the end of this. And I write my 3 bits of information, and I say, okay, let's go back to the beginning. And now I got to spin through 7,000 feet of tape to come back to the beginning of this, right? Really, really inefficient for just bouncing around from one spot to another. So there's sorts that take advantage of the idea that we don't want to move wildly from one location to another. So anybody here ever use SAS? Or hear of SAS? If you go into data science, you'll do SAS or R. It's the same idea. SAS was built largely around the idea of large amounts of data being stored in this kind of structure. And being able to make one pass through your data from beginning to end, pretty efficient. Being able to bounce back and forth to random locations, not so efficient. So there's different ways to code things like an insertion sort or a selection sort that minimize how much you have to move around from one spot to another. And we don't worry about this too much today because we have hard drives. And so this hard drive is spinning 7,200 times per minute, so 120 revolutions per second. But if our read-write head is sitting right here, and we want to read a piece of data that's located right here, it takes 120th of a second for that to spin around and come back to our read-write head. So there's still a penalty. And if we're accessing a bunch of information from here on back, once this comes under our read-write head, all the next pieces of information that we want are right there, ready to be read. So it's very fast. But if we want to read just totally random locations, piece here, piece here, piece here, piece here, hard drives suffer from the same performance hit that you get on a tape drive. So hard drives are arranged in a way so that you have this latency cost of getting your data to start appearing under your read-write head, but then once it's there, you can just keep pulling in bits, right? Same thing as a magnetic tape. It turns out we have this problem with memory too. We have random memory, and we can say, give me a location 20, give me a location 15,000, give me a location 17, and we don't have to wait for something physically to move, but we still pay the same kind of performance penalty that we have on these systems because we have this thing called cache. And cache memory, L1 cache, L2 cache, L3 cache, is a way to speed up memory access based on the idea that if I access data right here, most of my next accesses are going to be somewhere pretty close to that first piece of data. And if you write a program that accesses data here and here and here and just sort of bounces around your memory, it gets way slower than if you're accessing nearby, because you basically defeat the caching mechanism. So, yeah?
I was just wondering, is that how HBM memory works?
HBM.
It's like AMD was using it in their...
Not familiar with it, but most likely it's tied into something similar. I can look it up.
Because like I saw like the diagram, the memory was stacked on top of the chip itself.
Oh, okay, yeah. So different different solution, but similar problem, which is memory is always a bottleneck, right? Getting data into your CPU and out of your CPU is where most of our time and energy is spent. CPUs are really fast at chowing on data. You just got to keep feeding them. So yeah, moving the memory on top of the chip is a thing. So we have cache systems in our memory to take advantage of this locality. So depending on the architecture of your system, where your data is physically stored, the architecture of that storage medium, there's different reasons why you might do different sorts. So order of complexity is a big factor, but there may be reasons why a selection sort is going to make more sense than an insertion sort, or a bubble sort may be most efficient. And it depends on the nature of the data, how much is it sorted to begin with, how wide is your data, right? How much stuff do you need to move around, and what are you moving it around on? Are you sorting on tape? Are you sorting in a big memory, and so on? All right, so bubble sort, selection, insertion, all order n squared. Tomorrow we'll look at merge sort. Merge sort is an order log n sort, or n log n, and it's recursive, so we'll have fun with that. And then we'll start looking at some other sorting techniques. All right, I will see you tomorrow.